All right, let's take a look at our lesson for today. So today's lesson is on Riemann sums. Let's rephrase or remind ourselves what we've done so far. The lesson we talked about last time we talked about area under the curve. Remember that? We were working on area under the curve. We talked about how the area is between the curve and the x-axis. Then we looked at antiderivatives and talked about antiderivatives and integration, and we just did some indefinite integration, just to remind us where we were. Today, what we're doing, this technique, this Riemann sums, what this is a technique that we can use, and we are asked to use many times, in order to approximate an area. With integration, unfortunately, it's not always possible to integrate everything. We can take derivatives of anything, but it's not always possible to integrate things. So we have to have some techniques that we can use to approximate area under the curve. And this is one of them. These are called Riemann sums. And so the top pictures that I have up here, this right here, is just looking at the four kinds. These right here are really the Riemann sums. This is called trapezoidal sums. And so we're going to be practicing with those. So one thing I want to note, maybe we may or may not remember the area of a trapezoid. We would need to know that in order to do trapezoidal sums. But if you recall, it's 1/2 the height times base 1 plus base 2. And that's the formula for area of a trapezoid. And for what we're doing, we would consider this part right here. This part would be h, this width. And, this would be like base 1, and that would be like base 2. So we kind of need to think about it as tilted to the side, if you will. That's how we would calculate the area. We really wouldn't want to mess with trying to find that distance. So that's how we calculate the trapezoids, is we look at the distance along the x-axis is like the h, and then the height of each side of the trapezoid is base 1, base 2. Okay, so that just want to point that out. So let's look at what it means to have the right corner and the left corner and the midpoint. What that refers to is actually the height. All of these are just rectangles, and we know, there's several rectangles here. We know how to find the area of a rectangle. We've been doing that for years, right? Years. So how do we determine the height of the rectangle depends upon which kind of Riemann sum we're doing. If we're doing a right Riemann sum, that means the right corner of the rectangle would be what determines the height of the rectangle. That's going to be the height, would be the right corner. Notice how the left part is, not anywhere on the corner. So this would be a right Riemann sum, where we would take this height, the height of the right side of the rectangle, and that would determine the height of the rectangle in of itself. For left Riemann sum, it's the other scenario where we would take the left corner, and that would be the corner that we would use. We would use the left corner to determine the height of this first rectangle. Okay, so that's left and right. The midpoint is just kind of what it sounds like. What we would do is we would take the middle, the height at the middle of the rectangle, or the midpoint, and that is how we would judge the height of this rectangle, is by this y value, the y value at the midpoint. Okay, so that's the only way. These are all different. We're still just adding up areas of rectangles. Then on the trapezoidal sums, we've already talked about that. We would have to use the formula for the area of a trapezoid and we would calculate the area of each one of these trapezoids, and then we would add them all up. Okay, so again, what are we doing this for? This is a technique that we would use to approximate the area under the curve if we weren't able to do it, using calculus. Or even sometimes if we are, they just really like this technique, and you'll see it in lots of different scenarios. Okay, so first of all, I want to ask, is there any questions about these four kinds of approximation techniques I've talked about: the left Riemann sum, the right Riemann sum, the midpoint Riemann sum, or the trapezoid. Do we have any questions on that? Okay, so let's get to a little bit more specifics on these. Many times they will ask us if this particular estimate is an overestimate or an underestimate. That would be a normal question for them. And the way we would tell is by if the function that we are approximating the area of the curve, is this an increasing function or is it a decreasing function? Okay, that's basically what we would need to know. And so let's just investigate that. If we have a function that's increasing, in other words, as you read it from left to right, it's rising, and we wanted to do a left Riemann sum, let's just say we wanted to do the Riemann sum between 1 and 3. I mean, I'm just, whatever, Riemann sum between 1 and 3. And I want to do the left one. Okay, so that means that the left side would be what would designate the height of the rectangle. So the left side right here. And what I would do is I would find these areas, right? The areas, those areas right there. And I would use that to approximate my total area under the curve. Now, would this area calculation be an underestimate or an overestimate of the actual area? It's under, because you can see there's like some holes up there that we wouldn't have calculated that area. So what we need to know is that if we have an increasing function and a left Riemann sum, we're going to have an underestimate. Okay, an underestimate. Now let's look at another scenario where we have an increasing function. I'm still going to go 1 to 3 just because, I don't know, it doesn't matter. Now we're going to use a right Riemann sum. In other words, the right corner of the rectangle would be what we would use to approximate the actual height of the rectangle. And we would be finding all of this area right here and using it to approximate the area under the curve. So if I have an increasing function and I'm using a right Riemann sum, is that going to be an over or an underestimate? It's an overestimate. We can see visually why it would be so. Okay, it's an overestimate. Okay, are we okay on increasing functions? And so when they ask you this question, whether it's an over and underestimate, you have to, I'm just going to say this once, you're going to probably hear me say it a bunch of times. It's not okay to say, oh, because when I draw the rectangles, they stick up above the graph. That's not, they won't take that as an answer. You have to say it's an increasing function and a left or right Riemann sum, whatever, therefore it is a blank, over, underestimate, whichever it is. So you have to use this as your reason for why it's an over and underestimate. Okay, so again, we'll talk about that again. So that's increasing. Let's look at decreasing functions. All right, so we've got a decreasing function. I'm still just going to go 1 to 3 just because. I need to do a left Riemann sum. So let's see, we've got the left side is the height. So what we're looking at, and then the left side we've got here. So I would be calculating this area. And so if we have a decreasing function and a left Riemann sum, we would have an over or under? An overestimate. Okay, let's look at the right Riemann sum. Again, we'll just go 1 to 3. So I'm using my right top corner to determine the height of my rectangle. And so we would calculate these areas right here. And this would give me an underestimate. Okay. And again, our justification would be all about because it's a decreasing function and, left or right, that's why. Okay, so this would be our justification. We would have to use that in our justification of why we're saying what we're saying. Okay, so we've talked about why we use Riemann sums. We use them to approximate area under the curve. Now we've talked about how to determine whether we have an over or an underestimate. One other thing we need to talk about, and this is more rare, it's not as common to be asked on a trapezoidal estimate whether you have an over or underestimate. That's not as common, but we'll still look at it. So, and I'm hoping as we draw this, you can probably figure out, and again, we'll go 1 to 3, why not? So we're going to draw trapezoids, and the trapezoids would hook to the tops of each of those. So I have a trapezoid right here, and so we would find all of that area, and I think they're much more accurate approximations, a trapezoid versus a rectangle. But at any rate, in this case, if it was concave up, this estimation would it be an over or underestimate, do you think? Just a little bit over, wouldn't it? Just slightly over. So this would be an overestimate.
Wait, why is it overestimate?
Because since it's curved this way, since we're curved this way, when I do, the parts, like this will be more apparent. Let's say we had a trapezoid right here. You can see this little part right here would be over. It would be above the curve. We want the area under the curve, not the area above the curve.
Oh,
okay? And so when it curves down like that, we have a slight overestimate. Okay? And on the if the curve is concave down, let's go 2 to 4. Why not? Let's do that. So we would do, actually it'd probably be better. Let's do 0 to 1. That would be a little bit better. 0, let's do this approximation. So I would have this curve, we're looking here, which doesn't even really look like a trapezoid. It's really not. This side would be 0. That happens sometimes. It's okay. Then I would have this one right here. And then we would look at this area. And hopefully we can see if our curve is concave down and we're doing a trapezoidal estimate, then this one would be an underestimate. Okay, so what we've done is we've really talked about just an overview of Riemann sums and approximating areas under the curve and how we could determine whether it's an over or underestimate. Okay, are we okay so far? Okay, so let's do some examples. I'll do some examples that demonstrate what's going on here. So here we go. Let's go to our first one. Now, sometimes you'll have a calculator and sometimes you won't. So for this page right here, let's go ahead and use our calculator just to help us do our calculations quicker. And sometimes we will, sometimes we won't, but I'm going to use my calculator here. And so our first one is wanting us to do a midpoint Riemann sum. And on the interval 2 to 8, they want us to do 3 subintervals. Let's think about, first of all, what this means. A midpoint Riemann sum is using the middle point to determine the height of the rectangle. Right, and we're going to go from 2 to 8. And we want 3 subintervals, which means I want 3 rectangles. That's what this means. Subinterval means number of rectangles. That's all that fancy word means, is I want 3 rectangles. Okay, so if I have, let's see, 1, 2, 3, 4, 5, if I have 6 spaces, if you will, to do 3 subintervals, I would need the width to be 2. Right, you with me? I would need the width to be 2. So I'm going to have, one right here. That's going to be 1 rectangle. I'm just going to get me an idea. So I know that for midpoint, it's going to be this middle one that's going to determine the height of the rectangle. It's going to be the middle one. I'm just going to make this bigger for just a moment. It's the middle one that determines the height. And so you actually don't need a graph to be able to do this. I just think that it's a good like visual picture of what we're doing. So my rectangle would look, kind of like this, right? I would need to calculate the area of that one, which we will in just a moment. Okay, and then this one, okay, this middle one is going to be right here. And you don't have to draw the dotted lines. I just want you to understand what I'm doing. It's the midpoint that determines the height of the rectangle. So I've got these two. And then on my last rectangle, again, the middle point, this determines the height right here. So my last rectangle looks like this. Now notice how the curve is increasing and decreasing. They would not ask us whether this was an over and under estimate. They would not. Only if it was only increasing or only decreasing would they talk to us about that. So this one they wouldn't ask us. So, okay, so let's write this out. What's this is our function right here. So what are we doing? We are calculating. So I'm calculating the integral from 2 to 8 of f of x dx is approximately. That's what I'm doing. They really love for you to write integrals. You really need to write this first part. Okay, that's telling them what we're doing. We're calculating that. So the area of the curve is approximately,
On the outer ones in the curve, why did you do a rectangle? Why would you just do a triangle?
a what one, dear?
Like, why did you do a rectangle on the outside instead of a triangle?
Oh, because we don't have a choice. We have to do midpoint Riemann sum, which is all rectangles. We're not allowed to mix them. Yeah, we can't mix them. We have to do just exactly whichever one they tell us. And they never mix them. You're either going to do all, trapezoidal sum or all midpoint Riemann sum. We don't ever mix them. Even though you're right, I think it would be a more accurate approximation if we were able to do that, but we're just not allowed. Okay. So notice that the width, so we're going to just be, finding this area. I'm just going to highlight the very first one. I'm not going to highlight them all. We're finding the area of the triangle. Truly, it's really just a matter of finding the area of the triangle. So the triangle has a width of 2, right? It's 2 spaces wide. The height is whatever f of 3 is. And we're going to have to figure that in our calculator. I'd plug a 3 in. Plus. Okay, that's my first rectangle. My second rectangle is also 2 spaces wide, and the height of it is determined by f of 5. And that's what the height is determined by. My third rectangle is also 2 spaces wide, and they don't always have to look like this. I'm just saying these do. They're all the same width. And my height of my third rectangle is determined by f of 7. This thing right here is called the product and sums. You will get a point for writing that, but you have to show the product and the sums. You can't simplify as you go or you'll lose a point. I'm just saying that's a really big deal. The product and the sums. A really big deal. So we have to write that part. Okay? We have to write that part. So what I'm going to do is to find f of 3 and f of 5 and f of 7, I think it would be easier to use the calculator. Wouldn't you agree? Rather than plugging in the 3 and the 5 and the 7 and doing all that arithmetic. So I'm going to pull up the calculator and we're going to do that calculation in the calculator. Y'all okay with that? We're just going to work it in the calculator. So, and you can work this with me. So what I'm going to do is I'm going to store that function. So the function is 4x, and then it's minus, and I like having a fraction in there. So it was what, 1/2. You could use a decimal if you want to, it's fine. 1/2, and then that was x squared. And I'm going to store that as, I'm actually going to store it as f of x, just because it was called f of x, so I'll just keep with that. So f of x, we're storing it as that function. Okay, enter. So that's where it is. So now if I go to var, remember that f is there, right? So I do f of, what was it, 3? I need that number, that's 15 halves. I need f of, I need f of 5, and there's that number. And then I need f of 7. Okay, and that gives me those numbers. So I'm just going to do, again, I'm going to let my calculator do the work. So 2 times, I'm going to pull that first one down, plus, and then it was 2 times, and then I'm going to pull that second one down, plus, and it's 2 times, I'm going to pull that third one down, and that gives me my approximation. So I made my calculator do the procs and the sums for me. Are y'all okay with that? I just plugged that in. So we got 37. Just let me go back to the document. Okay, so that means that this is approximately 37, and we don't have any units to go along with it. So it's just 37. Okay, how are we with our first calculation of a midpoint Riemann sum? Are we okay? Okay. So now let's look at, we have another one. We're going to do a trapezoidal sum with the same, it's actually the same equation. Okay, so let me go down here. We're going to do a trapezoidal sum. So again, write your integral out. We're integrating from 2 to 8 of f of x dx, and this is going to be approximately. Now I'm going to draw the trapezoids. I'm going to make this a little bit bigger. So 3 subintervals means 3 trapezoids. I need 3 trapezoids from 2 to 8. So my first trapezoid to, let's see, my second one. So this is my first trapezoid. It would look like that, right? That's my first trapezoid. And then my second one would look like this. And then my third one would look really weird. It really kind of looked like a triangle, but we're still going to do a trapezoid. Okay. So let's just, I'm just going to focus on this first one. I'm going to highlight the first one. We're going to do all of them. So we're going to find this area. And remember when we were talking earlier that this is actually, this part right here is actually the height. I know that's weird, but that's the height. And this side would be base 1, and this side would be base 2. So that's how we would work trapezoids. Okay. So let's see. So my formula is 1/2 times the height. The height is 2, right? That distance between 2 and 4 is 2, times base 1. This is, it looks like a 6, but I'm not sure. So I'm just going to say it's f of 2 plus f of 4. We'll just use our calculator to make sure. Okay, I mean it looks like a whole number. It probably is, but I don't want to take a chance. That's my first trapezoid. Is everybody okay with that? Okay, plus. And just so that I can keep this graph kind of big, I'm just going to put the second trapezoid underneath, okay? Plus, then I have 1/2 times 2 times my next trapezoid is f of 4 plus f of 6. That would be my base 1 plus base 2. And then my third trapezoid, 1/2 times the same width, they're all width 2. My base 1 would be f of 6, and my base 2 would be f of 8. And again, that part, this part right here, is really important. You have to write that part. You can't just do it in your head, and you can't just write it on the graph either. I'm just saying, you have to write it out like that. Okay, you have to write that out. So what I'm going to do is I'm going to actually do that entire calculation in my calculator. Are y'all okay with that? Okay. Now the half times the 2 that's just 1. Can I not do those? Are we okay with that? Half times 2 is 1, right? So it'd be 1 times that plus 1 times that plus 1 times that. So let's go to our calculator. And so what I'm going to do is I'm going to do it all at once. F of, what was it? F of 2 plus F of 4. That's the first one. Plus, I'm just going to put it all in one string. Then F of 4. I'm doing the second one now. F of 4 plus F of 6. Okay, then my third trapezoid is F of 6 plus F of 8. Are you noticing any patterns about the stuff that I put up there? About these? You see that pattern right there? How this one is doubled, the ones on the inside are doubled? Does that make sense why they would be doubled? We'll look at the picture. So that's 34. And if you're like, no, I have no idea what you're talking about. Okay, look, see on this picture how this is base 2 of this trapezoid, but it's base 1 of this trapezoid. Y'all see that? See how that one side is included in both these trapezoids? Okay. So this would equal 34. All right, so that's our first experience with those kinds. Are we okay? Okay, let's look at this one. So the rate at which water is being pumped into a tank is given by the continuous increasing function R. Table of selected values for the time intervals given below. Use the following Reimann sums with the given intervals to estimate the number of gallons of water pumped into the tank during the 12 minutes. So now we're doing a right and a left. Okay, here we go. So a right Reimann sum. Now we don't have a picture, but I will tell you, you know I'm really visual. I really have to write this out as a number line. I just do. Because when it says 4 subintervals, this table just is confusing to me. I know some people have no problem with it. So really what I've got is I've got like 1, 2, 3, 4 rectangles. I mean, that's what I've got. And that's what I usually draw just to help myself. So I can kind of piece together what in the world's going on. Okay, you don't have to do that. I'm just telling you what I would do. So we've got, we're approximating, so we're doing the integral from 0 to 12 of r of t dt is approximately, and the width of all those rectangles is 3. We're doing a right Reimann sum, a right one, so I would use this height, that height, and that. I would use the right heights, right? The 3, the 6, the 9, and the 12. Okay, so let's do that. So the 3 was 13. The 6 is, isn't that lovely? It just stopped writing on me, just all of a sudden. Let's see if it will behave. I don't know. Okay.
Are all the heights going to be 3?
For this one, they are. They sure are. Okay, well, we'll just get out my extra stylus. Now, I will tell you, this example has even, they're all even, but that's not actually, to be honest, on the AP test, that's not kind of normal. Well, well, well. Neither one worked. Okay. So I'm going to pause the video for a second. Jeez. Okay, there we go. Ugh. Okay. All right. It froze. Who knows why? I don't even know. So 3 times, and then my next rectangle height is 18 plus 3 times. The next rectangle is 23 plus 3 times. The last rectangle is 27. Now, I will tell you, now this is good news. This is called the products and the sums. You have to write that. Notice how these are all numbers. There's no F of or R of, 3 or anything. If they're all numbers like that, that is an acceptable answer. You do not have to multiply and add stuff together. That's okay. The one up here, where we did the F's over here, that's not okay. You're not allowed to leave F of 3. You'd have to put a number there. But I'm just saying, like on a test, if you wanted to leave it like this, you could. I'm going to go ahead, and then you would write whatever the units are, gallons. That would be my answer. Now, in case you were wondering, or you maybe not wondering, it's 243 gallons. And this is a right Riemann sum, and this is an increasing function. Okay, think about that for a second. If it's a right Riemann sum and an increasing function, am I going to have an over or underestimate? In other words, is my approximation going to be greater or less? So let's think about that. We've got increasing. We're using the right ones. Do we see what that would be? You don't have to memorize it. You could just write it out. It would be an overestimate, right? So we're going to use the words they do. So we'll erase that product and sum. So it's greater than the true value because increasing functions and right Riemann sum. Okay. So the left one, I hope we get the idea of this. 0 to 12, R of t dt. It's approximately. So we would use the left endpoints. Okay, so for that one, we would use the 0. Let's use a different color. This one, that one. So we would use 0, 3, 6, and 9, those heights. So I've got 3 times 7 plus 3 times 13 plus 3 times 18 plus 3 times 23. And that would be, again, we could leave that as our answer, gallons. Or if you had a calculator or, wanted to do the calculations, it'd be 183 gallons. This is an increasing function and a left Riemann sum. So this is going to be, and we can even tell by the numbers, can't we? I mean, look at the numbers, 243 versus 183. Yeah, this is going to be an underestimate, or it's less than the true value because increasing function and left Riemann sum. Okay. Everybody all right? All right. So usually, I'll just be honest with you, usually students either love this because it's just kind of straightforward or they just hate it. It's like boring. I don't know. I don't know if we're in the boring range or in the I love this because we're just adding up areas of rectangles. I don't know. You're probably one of the other places, but we're actually just going to do this slide. We're not going to do the last slide because of the time. Okay. Now, let me just say, yes, I came up with that name. Yes, that was me. It was me.
That's so negative.
Okay, so it's because we need to tell the difference between the two kinds of Riemann sums. Okay, these are regular Riemann sums. This is what we're going to be dealing with. They're regular Riemann sums. The reason I call this scary Riemann sums is because I've taught this for a really long time and students are scared of this. I don't know. That's why I called it. But really, let's talk to you about what it is. And the chance that we're going to get one of these is not great. It's not great. It's rare. And usually it would be a multiple choice question. I'm just going to tell you. But we do need to talk about it. So do you remember way back in the day when we learned the definition of the derivative? Remember that? Okay, stay with me. Do you remember the definition of the derivative? What was that? Close. How do we find, what was the definition of the derivative? What did we do? Didn't we do a limit? Is that so far back in our brain? Remember we did the limit and we'd find the equation of the derivative and that was before we learned how to do all the rules? Remember all that? Okay. Limit as h goes to 0, f of x plus h minus f of x. Do we remember this? That? Okay, so remember the definition of the derivative was really hard, right? And then we learned how to do derivatives. Remember that? Okay, this is the definition of an integral. This is the definition of integral. This right here is the definition of an integral. Do we see that? The limit of the summation of all this stuff. No, we're not going to have to actually do the definition of an integral. No, we only have to just play with it in this little way. That's it. This is the definition of an integral. And you should be saying, oh, thank you that we don't have to do these by hand. Thank you, because it is intense. I promise you. Okay, we're not doing that. We're just going to learn, the only thing we're going to do is we're going to learn to go back and forth between these two forms. That is it. If I have it written in this form, I need to be able to write it in this form. If I have it written in this form, I need to be able to write it. I'm not going to have to work it out like that. There's no working it out. I just have to learn how to do go from one form to another. You with me? That's it. Promise. Okay. So, here we go. How do we do that?
Will we have to memorize that for a formula?
No. No. You're welcome again. No. No, you're welcome again. Okay. So,
Do we need to know those formulas?
for a formula quiz? No. Nope. For formula quizzes? No. No. So see, we should be okay with this. I'm just talking about the concept. Stay with me. We're just talking about the concept. So, I'm going to write this like the crazy limit thing. Okay, that's my first task. First of all, I want you to look at how this is formed. See how I have the limit, I have that summation, I have my function here, and I have my delta x. That's what I've got. Okay, let's start writing that. So we've got our limit. Again, you don't have to memorize these formulas. The limit as n goes to infinity of the summation. You do not have to memorize. If you're using it, I will put it on the test. K equals 1 to n. That's just the way they all start. All of them, just like that. Okay? We need to find delta x. Delta x is this formula right here. This number down here is A, and this number up here is B. That's what they are. A is the bottom number, B is the top number. So delta X is going to be B, I'm just writing the formula down, B minus A over N. In our case, delta X is going to be 6 minus 2 over N, right? 6 is B and 2 is A. That's 4 over N. Okay, that goes right here. 4 over N. What does that refer to? That refers to this part right here. The delta X is right here. That's the 4 over N part. I just wrote it down. The only thing we've got to do now is we've got to put the function in there. That's it. Just put the function right here. So how do we do that? Okay, so this X portion right here is created by this formula. Again, you don't have to memorize it. A is the bottom number, so 2 plus, and see how this number, this letter is a K? This formula was written if this letter were an I. So I'm going to take this right here, and this is going to be K, so I can match. That's it. Instead of putting an I, I'm going to put a K. Okay, that's it. So I have 2 plus K times delta X, which was 4 over N. And that would go in place of the X. So that would be squared. Minus 3. This is my answer. That is my answer. Uh-huh.
So if we don't ever need to learn the formulas on a test, would you give us that equation?
I would give you see the thing in this little dotted box right there? I would give you that. And I would give you that on a test. If you were going to do this problem, you would have the little dotted box, all that in the dotted box, and that thing I highlighted in yellow. Okay? Uh-huh.
Is C1 X?
Yes. You can, let's just, in fact, they like to do weird letters like that. Because see, what is this right here? That's a F of C. See how they have it written in code right there, F of C? This is really the same thing as X. Uh-huh.
I'm a little lost, so what is this for? Like you're rewriting it in summation notation, but why would we do that?
Because we need to learn how to go back and forth between, see this, I have highlighted in yellow, right up here. This is one form. This is the form that we deal with. This is the definition. Okay, we're just rewriting it from the practical one that we use, which this is the practical one that we use, to the definition. We're just learning how to go back and forth. We're not going to ever use the definition to find an integral. I'm just telling you, that is something else. We're not going to do that. All we're doing is going back and forth between the definition and the actual usable one, in my opinion. Okay? That's it. All right, that's the first one. Are we okay? So we've gone,
How do you know when to use the right endpoint or the left endpoint?
If they don't tell you, then always use the right. In the FRQ, that's this next page that I'm not going to do on the video, they want you to use the left. But if they don't tell you, we use the easier one, which is the right. Really, the only difference is the, K, plain old K or K minus 1. That's just the difference. All right, so now that we've gone that way, we're going to go backwards. We're going to go backwards. I know, isn't this so fantastic? Y'all are like, oh my gosh, stop torturing me. We're almost done. Promise. We're almost done. So we're going to go backwards. So now I'm going to turn this into an integral. Okay? Turning it into an integral. So what is this part right here? Right here, what is this? This is delta X, right? That's what it is. So delta X, so I have 6 over n equals, and delta x was, what was it? B minus a over n. That's what that was. That's delta x. Okay? And what is this? What is this? That's this. See, that number is that. And what is that? That's a. Okay, so 6 over n equals b minus 4 over n. So now I can just solve for b. So the n's go away. I have 6 equals b minus 4, so b is 10. Okay, so I've got the integral from 4 to 10. This is most of my battle. Most of my battle is done. Now I need to figure out what was the function. I have to figure what was the function. What did we put in place of x? We put 4 plus 6k over n in place of x. So what was the function? It's that squared, right? It's x squared. That's it.